let's remember our paradigm that we're trying to describe. So we had a box with a button on it, and we press that button, and then something happens inside the box. There could be an atom in there. We know it started out in some thermal state. We wait some amount of time, and we have some idea of, we know we can assign some density operator rho to describe this invisible system that's exiting the box. Okay, or this hypothetical system. I shouldn't say invisible, hypothetical. Okay, we have a hypothetical system leaving the box. We know later on it will trigger a measurement outcome, okay? So it's not that hypothetical because it has concrete causal influence on things we can observe. So calling it hypothetical is a little bit of a cavalier thing to do. Okay, it's a physical system, leaves the box. The transformation, we can set a dial which transforms the state. So here we have rho, here we have rho prime, and here we have rho double prime. So our preparation, we decided that the most general mathematical object you need to make the best predictions you can about where this needle will point is an object which is an operator acting on the Hilbert space called a density operator. In the simplest case, when your preparation is ideal, this density operator reduces to a projector, and then we recover the usual, undergraduate description of quantum mechanics. And a projector is essentially, if you ignore the global phase of the wave function, the projector is in one-to-one correspondence with the physically distinguishable set of quantum states. So let me just write that down as a reminder. If the preparation is ideal, then rho is a rank 1 projector. And we can associate this with a vector, the vector psi of arbitrary phase with an arbitrary phase. Okay, so we have this equivalence class of phases. Alpha is just some complex number. Alpha is just a real number. Okay, so we recover the usual wave vector description only if we have an ideal scenario, if we have maximal knowledge about the preparation. And so that's what you learned in undergrad, was how to describe quantum mechanics using this object. But we want to promote it to the outer product, the projector, and that buys us a greater generality. And then, of course, if the preparation is not ideal, then we get essentially convex combinations of these projectors, which describes our set of density operators. And now, what I did last lecture is I skipped over the transformation, and I said, what's the most general operators we need to describe what's going to happen in this box? So then I was giving you examples of measurement procedures which require this more general description of a POVM, as opposed to just the self-adjoint operator A, and in particular its decomposition into projectors, its spectral decomposition into projectors. So you could think about ideal quantum measurements as a self-adjoint operator, or equivalently as the projectors into which it has a spectral decomposition. So you think of a PVM, which is a set of projectors. But the most general thing is you have a POVM. And so I was giving you examples of situations where you need this more general description. And the very last example I gave you was von Neumann's indirect measurement, in which, now the reason for von Neumann's indirect measurement model is to start thinking about this piece, what happens to the state after measurement. Okay, now we're not ready to discuss that in detail yet, but I alluded to it, so I just want to warn you that we're going to come back to that. How do we talk about the state after measurement. And von Neumann's indirect measurement model is designed to analyze that problem. But there's two parts to measurement. One is explaining the probabilities of getting different outcomes. We hear the outcome is a pointer position. Outcome K is a pointer position. On this apparatus. This dial is, of course, the setting which chooses which measurement you're doing. It chooses the POVM. So this dial, you choose the POVM. You choose this set. And then once you've chosen the set, you press this button. The light goes off. The pointer takes on some value, which is your outcome. So let's just stick with that language, okay? So this is the outcome. And then you have a state. Possibly, there are scenarios where you want to talk about the state after measurement. Now, there are measurement boxes where there is no output. So you don't get the state after measurement. But there are certain kinds of measurement where you can talk about the state after measurement. And we're going to describe that. And that leads into these kind of interesting discussions about, I mean, this is the part that has been a source of interpretational confusion. Okay, the collapse of the wave function and all that. That comes in here. But we have to set the stage to discuss that intelligently. Okay, so let's first go back and talk about transformations and describe this set of objects. And then we'll come back and talk about state update rule. So in the recap for the measurement, so preparation. And then here we have measurements. So let's just recap what we saw for measurements. So for measurements, we have, in general, it's a POVM. And the probability of outcome K is equal to the trace of EK rho. And then in the ideal case, EK is equal to a projector, pi k, so that's a projector. But in the general case, EK satisfies two conditions. It's non-negative. And it sums to identity. So the summing, okay. So the summing to identity means you're describing a situation where this light always goes off. Now, of course, that's not always the case. You can have, remember I talked about the photodiode, the photodetector. You know, if another photon arrives too soon after the last photon, then there's a dead time in the response of the detector. So the detector might not click at all. If the detector doesn't click, it means this light doesn't go off and the pointer doesn't move. So that corresponds to no outcome. So there you actually have to subnormalize this. So there you'd actually have a situation like this. Okay, so where the inequality accounts for the possibility of no outcome. When I say no outcome, I mean you press the go button and you wait what you think is a long enough time and you find, hey, where's my click? My light didn't go off, my pointer didn't move. So, you know, either someone put a piece of cardboard in here and didn't tell you about it to block the beam, or maybe a piece of metal, depending on what it is, if it's a neutron. You know, or there's a malfunction here, or your detector your detector malfunctions, things like that. So in general, we can accommodate that by adding an inequality here. But that's kind of a technicality. It's not an important, it's a normalization issue, really. And then this first condition is designed that you get probabilities you get real numbers that are probabilities. If EK is, if we drop this assumption 1, then this can be a negative number. And of course, there's no well-known meaning to what a negative probability would be. So that's why we impose this condition. Okay, good. Now let's talk a bit about transformations, and then we'll come back to von Neumann's indirect measurement and the update rule after that. Okay, so for transformations, so we're going to have the same story as we had in the other two cases. What does it mean to have a generalized transformation? Well, one scenario, as we've seen in for measurements, for preparations and for measurements, is you can have what happens in this box is that there's some probability P that it applies some unitary U1. And there's another probability 1 minus P that it applies a different unitary U2. And so then you have a probabilistic description of what's happening inside this box. Okay, so case 1 is we have a probabilistic mixture of unitary operations. Probabilistic mixture. I mean, this is kind of a trivial case, but it's worth being aware of unitary transformations. So there we would have rho prime is equal to P U1 rho U1 dagger plus 1 minus P U2 rho U2 dagger. So here P is some probability. Okay, and so we can think of, like, we can define some mathematical objects we'll call Krauss operators. Where we define A1 as the square root of P U1, and we define A2 as the square root of 1 minus P U2. Okay, then we can describe, then we just have the following description. Sum over K, A sub K, rho A sub K dagger. Where here I'm allowing the sum to be free, so now I have various probabilities of various U sub K's. So this would be P sub K, U sub K, just to generalize the probabilistic combination, where each A sub K is equal to a square root of P sub K, U sub K. And now we have a model describing arbitrary mixtures. So this is our new model for transformations, is we have, so the new model is that transformations are described by a set of operators A sub K. And we remark that what they have to satisfy the fact that the sum over K of A sub K dagger is equal to identity, such that. Now, where does that come from? Let's make sure I put the dagger on the right one, which I may not have. So how do we see this condition? I have to remember. It's trivial, I know. What is it again? Does anyone remember? You guys may have seen Krauss operators.
Yes, we have to prove that on our homework due to Friday.
Oh, this is a homework proof. Oh, good. I won't show you then. Great. So did I get the dagger on the right?
Yes.
Because it turns out, as you will see, it turns out, now it turns out Aggie said, read this assignment so you make sure not to answer it in class, and I've completely. It turns out that for case one only, and this is true for case one only. We're going to do a case two in a moment, which is not true. For case one only, it's also true that the sum over k, ak dagger is equal to identity. Did I get this? Am I getting the dagger on the right? I can never. One of these is the unitality condition.
Yes.
This is unitality?
Yes.
Okay, good, perfect. This is called unitality. So what this means is that if I start with the identity state, I end with the identity state. So this operation leaves the identity input state invariant, which makes sense because each unitary is going to take identity to identity, and a convex combination of identities is just identity, right? But when we're going to look at case two in a moment, we're going to see that this condition holds. Okay, so this is homework. Check this. So do this at home or in the bistro, wherever you like to do your assignment. Do this at home. Or verify this. When I say do, I mean verify. And then I think you should also verify this. It's trivial, but just to verify this too. Okay, so that's simple. Now we're going to look at another scenario where we have generalized transformation, and we're going to discover that this model completely describes that situation as well, but we have to drop this assumption. Okay, so case two, and case two is now we're going to think about, so case two is going to involve inside my box here, what's going on is, my system comes in, and this box, unbeknownst to me, has a secret back door. And in that secret back door, it's coupled to another universe, or our universe. Parts of the universe that we can put it inside the box, by the way. I'm just being funny. So look, you can, or trying to be funny, I should say. So look, the point is, we can have other quantum, so let's suppose rho is a spin-half particle. It might be that I bought this box at Best Buy, and it includes a whole bunch of other spin-half particles inside it. And then when my spin-half particle goes through here, this box actually couples the spin-half particle I gave it with the spin-half particles it already had inside it, allows them to interact in some way, allowed by quantum mechanics, unitary operations, on this extended Hilbert space of two spin-half particles. And then it spits out one of them, I won't know which, out the release door. What can happen? What's the most general mathematical model that it can describe the kinds of transformations that can occur under that situation? All right? And so this, by the way, is a model of decoherence. Okay? So this is all you need to know about decoherence as well. So case two is that we allow our system of interest which we'll call HA, to interact with another quantum degree of freedom. So because it's a quantum degree of freedom, I have to assign a Hilbert space to it. So I'll call this is the state of my other system, and it's an element of the linear operators, well, it's an element of the density operators on some other Hilbert space HB. And then we also have the fact that there's going to be some interaction Hamiltonian, which is going to couple which is an element of the linear operators on HA cross HB. Okay, so I'm doing things with my usual level of abstraction. Let's just look at a concrete example. What that means, for example, we could have H int equals A SZ cross, this is my particle A, cross whatever, SZ, here, let's make it of system B. Okay, so this would be 2 spins. Interacting under some scalar interaction strength. Okay, so there's lots of ways to do this. You can couple an atom to the electromagnetic field. You can couple anything. You can couple a spin to angular momentum, couple spin to the in the Stern-Gerlach apparatus, we were coupling the spin degree of freedom to a momentum operator, which gave it a momentum kick. So there's lots of examples here. I mean, here this is the complexity of describing quantum systems is that full complexity is here. So this is just one very simple example. Right, so we have some interaction. So typically what it might be also in the decoherence sense is you're describing some atom, you've got it trapped in a nice magneto-optic trap, you're doing experiments on the atom, but then your grad student didn't do the best job of waiting for the vacuum to be perfect, so there's some dust particle floating around, and here you're doing these complex laser transformations to manipulate your atom, and this dust particle comes by and bounces off your atom, and then goes away, and you never see it again. Well, that's going to have an impact on what you do. All of a sudden, you're going to see that what you thought was a pure state became a mixed state. Right? So that's a coupling between the atomic energy levels and some recoil, some scattering off of the dust particle. So some position operator for the dust particle, and some raising operator for your or lowering operator for your atom. Okay, so there's lots of things that can happen here. So let's remark that this is this is an example of decoherence. This is an example of decoherence. Let me say that. This can be. So decoherence being generally the loss of coherence due to coupling to another quantum system. I'll take your question in 1 minute. I just want to make one more comment. Notice that the system in HA is interacting with another quantum degree of freedom, right? So I just want to contrast this with case 1. Case 1, different unitary operators were applied based on some coin flip. I flipped a coin and I decided whether or not to apply U1 or U2. So the point is we can just have a classical description of the coin in order to account for this. So what I mean by classical is that the transformation is unitary with some probability. The resources I need to implement this is a random number generator, which is a classical device. Of course, it's not a true random number. It's a pseudo-random number generator, I should say. And then here, we have some quantum degree of freedom, which means that I can lose coherence to this quantum degree of freedom. I need a Hilbert space associated with it. So there's a conceptual distinction to be made there. And in fact, when you allow this coupling, this is exactly when you can violate this condition, when you have a quantum degree of freedom. The questions?
So, kind of alluded to this, but should I expect that I can always get this by appending to my Hilbert space a larger Hilbert space and ignoring part of it, the same way I would be able to get like a mixed state from a bigger pure state and tracing over as part of it. So assuming that...
Are you saying, is case 1 subsumed by case 2?
Can I always...
Yes. The answer is yes. I mean, we have our standing hypothesis, gravity notwithstanding. Our standing hypothesis is that we can describe all systems quantum mechanically. And that when we describe something classically, that's a special case where you don't need the extra mathematical and conceptual complexity of quantum theory. You can just replace things with probabilities and so on. But yeah, in principle, I can always simulate this with that setting.
Right. Well, so when you say simulate, it's like
realize.
From like flipping a coin, but you give me a quantum mechanical description of the coin, then this falls out of that.
Yeah. So it's actually a hard problem to show that, but it's true. We assume it's true, and in certain cases you can show that it's true, that we just take like, basically you would take diagonal density matrices on system B, and the interaction would commute with the eigenbasis in which system B is diagonal. So everything's going to be basically diagonal in HB, and that's essentially enough to simulate any classical stochastic process, roughly speaking. So yes, you can, but it's non-trivial to show it.
So you constructed the cross operators in terms of the unitary operators there,
Mm-hmm.
right? It's similar as we did with the POVMs constructing them with projectors.
Right.
So, but if I take a set of cross operators, the only condition that they have to satisfy is this one, right? They sum up to one.
Mm-hmm.
Okay. So is there, for any set of cross operators, I can associate it a unitary operator, such that if I make the evolution like this, it's equivalent to an evolution, a unitary evolution.
Can you repeat the question?
So if I have a set of cross operators,
Mm-hmm.
right, and you're saying that your transformation is like that on row prime, right?
Mm-hmm.
So this is if for any set of cross operators, I can always find a unitary evolution that does exactly the same.
No. The answer is no. So the question was, if I have some set of cross operators, can I always think of it as some probabilistic mixture of unitary operations?
Yeah, I mean, if you can.
And
Yeah.
and so the answer is no, because specifically in case 2, we're going to get a set of cross operators which will satisfy what's in the box, but will violate this extra condition. So this extra condition will always hold if you have a probabilistic combination of unitaries. But this extra condition will not hold if what's going on, if my cross operators come from the fact that I've interacted with some other quantum system. And to give you a concrete example of when that happens, it's possible to have quantum transformations which take the identity state and give you a pure state back. So think about the fact that I know if I take some atom and I put it in a box, and I start out in a uniform superposition of some set of eigenstates of the atom, not a uniform mixture. So I have a probability of being in the ground state, I have some probability of being in the excited state, and so on. These might be thermal probabilities, but let's imagine it's the identity state, so they're equal probabilities. We know that if you wait some time, physics tells us that atom will decay to its ground state, which means I started in the identity state and I was left in the ground state. That process, that physical transformation, can never be described by a convex combination of unitaries, because the convex combination of unitaries always takes the input identity state to an output identity state. So I can't describe spontaneous emission with this model.
Okay, but now in the case 2.
With this model, and yeah, this model.
Okay, in case 2, you have an interaction between subsystem A and subsystem B, right? So I can associate a unitary evolution to that interaction.
On the bigger Hilbert space. Yeah.
I can construct a cross operator from that unitary evolution.
We're going to get there, yes.
Right. So my question goes in the other side. Even if I'm in the bigger Hilbert space, any set of cross operators can be constructed from a unitary evolution?
Okay, you're jumping ahead. We're going to get to that. So I'm going to give you all of that knowledge if you just let me continue. Yeah. Okay. Are there other pressing questions? Yeah.
I don't know if this is similar to what Andreas was asking, but so this example you just gave with the spontaneous emission, could you always append your Hilbert space and make it big enough so that you could model it as just a unitary?
Yes, you can always, yes, this is called Neumark's dilation theorem, which we're going to discuss in a moment, okay? Okay, so, all right, so where am I? So we're discussing this case 2, in which we allow our quantum system to interact with another quantum system via some arbitrary interaction. And then we want to say, what's the most general way to describe that transformation if I'm limiting myself to describing it as an operation on my system of interest, right? So that's a choice of description, right? No, I can always think about everything as being pure and unitary with projective measurements if I'm willing to include other degrees of freedom in my description, and so my Hilbert space can grow really, really big. It can involve all kinds of things like dust particles and planets and giraffes. And if I include all of that in my description, I will have a unitary description. But in practice, I don't want to describe the giraffe down the street. I just want to describe my spin-half particle. So what's the most general operation what's the most general mathematical model that describes the transformations on that Hilbert space of interest, right? So that's an important point, is that we're forcing our description to be a description of operators in a particular Hilbert space, which is associated with the system we're interested in, whether it's a spin-half particle or the position of the particle or whatever it is. Okay, how do I do this? Okay, it's in my notes. I could check my notes, or I could do this from memory. Which one's going to be? All right, I'll check my notes. I'm always impressed when lecturers can give their whole lecture from memory, but sometimes, depending on how much sleep I've had the night before, I may or may not be able to do that. All right, here we go. Okay, so now we have HA cross HB, and we have some unitary, which is an element of this bigger Hilbert space. And in general, that unitary will be something like HA tensor identity. Yeah. Plus identity cross HB plus HInt. Okay, so the point is our system is evolving as it goes through this box. There's a term which corresponds to just some Hamiltonian affecting the system I put in there. I sent in through the door, through the entrance. And then there's another, I promised you there's another quantum system in there somewhere. And that can also be evolving in some way. And then the critical term is this interaction term. Without it, if in the absence of this, we can just ignore everything and we just get unitary evolution on the system of interest. Okay? And then we're just gonna do this in general and just say we have some unitary, and we're not gonna worry about its realization in terms of a Hamiltonian, but this is just to give you kind of context. You're probably used to seeing Hamiltonians, and so this is what it would look like. So then we're gonna have the output, rho prime, is gonna be equal to, we're gonna use capital lambda as our symbol. Here, let's add time, because that's always good to have. Let's just call this rho a at time t. And then we have lambda corresponding to the time t that the particle is in the box. We can make this a discrete time. It's a discrete time transformation, so time is just a token here. But in general, we can have continuous time transformations, which we'll touch upon. And then rho a at time 0 is the state going into the box. Okay, so my notation has changed a bit. Maybe I should be consistent in the notation so that it's clearer. Let's just do that. And then hopefully the fact that I've added an a here doesn't trouble you. So that's rho a and that's rho a prime. Okay, so this is our operator. It's called a super operator because it's an operator. It's a linear operator on the space of operators. So some people put a double hat on there to remind themselves that it's a super operator. And then we know how to describe this because you've learned about the partial trace, right? So the point is we know that what's going on here, and this is going to be a packed statement, is we have the following situation. We have UAB rho a tensor sigma b U dagger. So this whole piece inside the brackets is just some rho AB prime, right? So here, what's inside the brackets, I'm just describing, my goal is to describe things just using my Hilbert space of my system, but I'm taking into account the fact that there's some other Hilbert space inside the box. And so I have a unitary transformation in my extended Hilbert space, which produces some quantum state, possibly entangled, possibly separable, of my joint system. And now all that comes out of the box is my spin-half particle, or my system of interest more generally. So I want to take a partial trace. So the idea here is that rho A prime is equal to the partial trace of rho prime. That's what's going on there. So now what I'm going to do is I'm going to evaluate this expression. So to evaluate the expression, trace over B, rho A prime is equal to a sum over the orthonormal basis associated with B. Thank you. Okay, so that's pretty nasty. I still can't evaluate it. Now I'll use the fact that sigma B admits a spectral decomposition. So sigma B is equal to a sum over L, some eigenvalues lambda L, LL. And I'll insert that. So then I get rho A prime is equal to sum over K and L of K UAB L lambda L rho A L UAB dagger. Okay. Now it's important to recall that K UAB L is not a scalar. K UAB L is actually a linear operator on HA. When I say equal, I mean is an element of. Okay, so let's define some linear operator AKL as K UABL then we have rho A prime is equal to a sum over K. I made a mistake. I need my lambda L here. Just so you know, in my notes, I assumed sigma B was a pure state. So this extra sum is being added ad hoc here. It's more general anyways. So we include this square root of, remember lambda is a non-negative number because sigma B is a density operator. Now I think I want to, no, sorry. So I have to think about this extra index because it's not in my notes. So I'm trying to remember the right way to do this. So let me write it out more carefully, which probably helps you guys anyways. So I have a sum over L of AKL rho A AKL dagger. And yeah, I need the double sum. Okay, good. Okay, so now we have, so now our transformation, our general description of this transformation, which is the most general thing we can imagine in terms of our ideal axioms notice that we can always, remember as I showed you, whenever you have a mixed state on HB, you can think of it as a pure state on a bigger Hilbert space. Everyone remembers that? Great. So what does that mean? That means the greater generality I've included here is actually not greater generality, right? Without loss of generality, I could have just assumed that sigma b was a pure state by just imagining HB to be a bigger Hilbert space. For how many of you is that clear? Because that's a bit subtle. Just a few. Okay, so anyways, let me just write this out. Let me finish my sentence, and then I'll get on to the subtle point. So this is our set of transformations, and then you can check this. The sum over KL of AKL dagger, AKL equals identity. Basically, you should check this. Okay, you can verify this on the homework or for fun. And it follows from the fact that U is unitary and these guys are normalized states. It's not hard. Okay, so that's our picture. But let me give you some comments. So remark, in general, it is not the case in case 2 that the sum over KL, AKL, AKL dagger is equal to the identity operator on A. Okay, that only works for case 1. And this is going to allow us to describe the spontaneous emission of an atom. So we can go from a state of high entropy, a mixed state with large von Neumann entropy, to a state of low entropy, such as a pure state, a ground state, say, by considering this scenario. So here's something that puzzled me for a number of years. It's a little paradox, which the answer is on the board. So, you do quantum mechanics, you learn about the atom, and you write down your Hamiltonian for the atom, and you start out in some superposition of the atomic states. What do we know happens physically? We know the atom will decay to its ground state. It will evolve into that ground state. So if I start out in a mixture of energy eigenstates of the atom, and I evolve under the Hamiltonian for the atom, that mixture is going to stay a mixture. It will never evolve into the ground state. So what's missing in my mathematical description of that atom that allows me to have a formalism which accounts for the fact that we know it's going to decay to its ground state? What's missing? Exactly. The interaction with the electromagnetic field. So you have to include in your atomic description your Hamiltonian. You have your Hamiltonian for your atom, and then you have another term. You have a Hamiltonian for the electromagnetic field, and then you have a coupling between the atom and the electromagnetic field. And it's this coupling which makes it that the eigenstates of the atom are not eigenstates of this whole Hamiltonian. So that's what allows you to include spontaneous emission, for example, in your formalism. It's that coupling. All right, good. Now there's another remark I promised you. So this WLOG means without loss of generality, I can assume sigma b is equal to some pure state, which I'll call 0. Okay, why is that? This is true because I did not specify the size of HB. And our purification theorem, told us that given some sigma b, which is an element of the density operators on HB, I can always construct a pure state psi, which is an element of the density operators on HB cross HB prime by just adding more Hilbert space. So I can purify my mixed state. And now I can just redefine HB to be HB cross HB prime. All right, so that's just a mathematical trick. In practice, if you have some concrete Hilbert space, if you specify the Hilbert space of system B, like you say, hey, my system B is a spin-half particle, I know that. That's what I want to describe. Then you have to include the possibility that the state of the second spin-half particle can be a mixed state. But if I'm working under the scenario where I'm just talking in the abstract and I don't really know what HB is, then I can always assume, if I allow HB to be arbitrarily large, I can always assume, well, not arbitrary, but large enough, I can always assume sigma b is a pure state, which means I can drop this spectral decomposition. Lambda L becomes 1 for L equals 0, and 0 for all the other L's. And then, so this disappears, sum over L disappears, and I just get a sum over K, AK rho A, AK dagger. All right, so that's kind of it's a special case or a general case depending on what assumptions you're making about HB. Is that better? How many more have you got it the second time? Half? All right, the rest of you, I think you can either ask questions or think about it when you're brushing your teeth. Yeah?
So when we enlarge the system to purify the signal B, could it be that the evolution of the enlarged system is not unitary? It could be an open system, and then this description will no longer hold. So
that's true.
I mean,
Well, look, I mean, here's the thing. We're trying to describe general transformations. And what we're doing is we're building it up from our basic axioms. So our ideal axioms are that, transformations are unitary. So, I mean, you're kind of getting into this cyclic picture where I can't define general transformations in terms of general transformations on HB, right? Otherwise, it's circular. So let's assume that there exists some Hilbert space on which we have a unitary transformation. And then we find that the most general description is one of these maps that I've just defined for you. So our general description then is that, actually I should write this. So this now is our general model of transformation. And now once you've accepted that this is true, then I agree. Then you can say, okay, well, maybe my transformation on system B is actually some set of Krauss operators.
Yeah,
sure.
I'm fine with this description, but I'm saying when you want to purify your B.
Right. Oh, yeah. That the general transformation on that purified. Yeah. Right. So there's two purifications involved here. Okay. So there's a purification that guarantees that your initial state of your ancilla system B is pure. So I have to increase my Hilbert space. I don't have to. I can choose to increase my Hilbert space so that sigma b is just some pure state. And then you say, aha, well, maybe sigma b is a pure state, but I still have some mixed transformation acting on that. Well, then I can just purify again. I still have a pure state for my sigma b, but now my mixed transformation on B becomes a unitary transformation on HB cross HB prime cross HB double prime, and then just define HB to be that bigger Hilbert space. I've got a pure state, and I've got a unitary transformation. But you haven't seen that second dilation theorem yet. I'm about to promise it. I'm about to give it to you. So again, when I finish this lecture, I think your question will be answered.
One thing here, I don't see why the unitality condition is not satisfied in this case.
Good.
I mean, if I plug those operators there and use the completeness relation of the basis of B, it satisfies the unitality condition.
You're claiming that it does satisfy this. No.
If I take just sum it. I mean, take that sum, AKL dagger, right? If I use the completeness relation for the L's, right, that goes into unity.
Well, forget about the L's. I mean, if you can just show it for, if you can just show it where sigma B is pure.
Right, no, just
get it the wrong.
Oh, did I write the wrong?
You got the other one.
No. This is, you promised me that this was unitality. This is violated. So not, i.e.
I don't see why it's violated.
Well, good. Then look, I know I'm right. So I think rather than bore you with a calculation, I think you should just do this calculation yourself. And if you can, this is not a case where I have any doubt. This is certainly. Anyways, we can discuss it after class, okay? I want to keep going. So just when I'm claiming this is true, and I think that this is the kind of thing that's a good homework problem. So I'll let you verify this on your own as homework. Okay, so now let's give you some general terminology. So basically, based on this remark, in general, I'm going to replace that box with a simpler box. In general, our transformations take the form lambda rho is equal to a sum over k, ak rho, ak dagger, such that we require that the sum over k of ak dagger is equal to identity on system A. And we call lambda is called a CP-TP map, which is a completely positive trace-preserving CP-TP is completely positive trace-preserving. Now, there's a huge number of things I can tell you. There's a huge number of examples I can give you. I give a whole course where I spend a month just talking about these things. So I have to kind of pare down what you're going to learn here. Let me just give you some general highlights. Okay, so first of all, the operators AK are often called Krauss operators, after Krauss, who discovered them or first introduced them. Yes?
Does the lambda have a name?
No. This lambda here? The capital lambda.
The super operator.
Yeah, so it's called a CP-TP map. Or it's also called a super operator. It's also called a dynamical map, a general quantum operation. It has a lot of names. There's the Krauss operator. So basically, for a given for a given, whoa. One time I write the word quantum out in full, I misspell it. That's funny. All right, so for a given quantum transformation, lambda the corresponding decomposition, the corresponding set of operators AK is not unique. Okay? So there's more than one choice of operators which correspond to the same physically indistinguishable set of transformations. Is not unique. And I'll just remark for terminology, any given set AK is called a Krauss operator decomposition. Yeah?
Is it not unique because it depends on the basis you chose for the usual
Yeah, I think there's at least for that reason. There might even be more reasons, but
okay, but like in this example.
yeah.
Okay.
What else do I want to tell you? We can describe scenarios where systems are lost by subnormalization. Okay, so the inequality here allows for the possibility that I lose systems, in which case lambda equals lambda rho equal to sum over k, ak rho, ak dagger is CP, but not, it's completely positive, but not trace preserving. There exist better representations of lambda. When I say better, I mean easier to work with. Better than the Krauss one, than the Krauss decomposition. The Krauss, it's called the Krauss operator sum decomposition. Check, check. Okay, great. So of course, I give a whole course on this, and the Krauss operator sum decomposition. So it turns out that I think that for historical reasons, people always talk about Krauss operators to describe completely positive trace-preserving maps. Our axiom is this. Our generalized axiom, did I make transformations axiom 2 or 3? Anyone remember? Well, for transformations. Our generalized axiom for transformations doesn't refer to Krauss operators, which is basically the allowed the possible the set of possible okay, so this is an axiom that's false, but here you have it. The set of possible transformations on a quantum preparation rho is the set of CP maps lambda so here's an axiom that, okay, so first thing you have to learn as students is what does everyone else think, and then what's actually true. So this is what everyone says, and unfortunately it doesn't account for the same situation. I brought this up earlier, right? That what was involved in our derivation here, what did we assume at the start in this derivation? We assumed that sigma b had no correlations with the state that went into the device. Okay, so that sounds totally plausible, but unfortunately, things don't happen that way. When you have some quantum system, it's hard to control them. The way that you prepare the quantum state is, in general, going to be imperfect. It's going to leave a signature of what you did, a history, some memory of what you did is going to be written on some environment around that system. And that environment can come back and affect the system transformation. So you get a nonlinear response happening where the actual transformation the system sees depends on the way in which you prepared it. We haven't accounted for that here. And when you allow that possibility, you get a very complex situation which no one has yet figured out how to describe in a nice way. So this is an open problem for research. It's a highly relevant problem. And in that case, the assumption of the map being completely positive fails. Moreover, the assumption that quantum transformations are linear fails. So in general, so I'll put an asterisk here, and I'll say this is true assuming sigma b is uncorrelated with rho a. Okay, so that's the caveat. And it turns out this assumption is typically not met. But only visible, but only noticeable in the limit of precise measurement of high precision measurements. / control. So this is so a CP map lambda is linear, which means that lambda of P1 rho 1 plus P2 rho 2 is equal to P1 lambda rho 1 plus P2 lambda rho 2. Okay, but correlation between sigma b and rho a violates even linearity. Violates linearity. So this property, So not just the complete positivity is lost, more precisely, it's the linearity that's lost. And of course, all of quantum mechanics is built on this edifice of linearity, which is what makes it mathematically so trivial. I guess I shouldn't say that to you guys, but yeah, I mean, the amazing thing about quantum mechanics, as conceptually deep and subtle as it is, mathematically, it's one of the easiest theories you guys will learn because it's just linear algebra, right? You know linear algebra, you know quantum mechanics, especially in the finite dimensions. If you're dealing with finite dimensional systems, quantum mechanics is mathematically, the mathematical framework is second-year linear algebra, basically. I'll agree that infinite dimensional Hilbert space gets a bit subtle. There's some functional analysis in there, which is non-trivial math. Yeah?
Does this mean we can tell how people prepare states in the lab? We can tell the difference between two different decompositions of an estimator?
That's a clever question. I don't think so, but I can't see why. I'm pretty confident that it can't. Okay. Yeah. I mean, you know, actually, maybe it can. Maybe that's a subtle question. Probably, if you set up the problem the right way, you could actually. Now that I think about it, but it would involve essentially you have a flag that's set. You know, one decomposition leads to one imprint on the environment. Another decomposition leads to another different imprint on the environment. So then there's information about which way you prepared the system in the environment. But it's kind of cheating because then the point is the real state of the system is okay, you know what? Let me think about that. Actually, I don't know if I can answer that just from simply. Yeah.
Sort of on the point of the sigma being role will become correlated in principle because just preparing your environment and the sigma be. But I think in practice, what would I have to worry about? I mean, what is one case? Is there a simple case where an experiment is being done where this could happen? I can't picture it.
Sure. Sure. Okay. So, I mean, okay, that's a very good question. That would be a great example. It will take time to answer that question. Let me sketch the answer so I don't spend too much time on it, okay? And hopefully it'll be sufficient for, basically, suppose I'm preparing.
Can you repeat the question?
Oh, sure. So the question is, can you give a kind of a concrete example of where this might occur, that this correlation, the correlation might happen, like some physical mechanism that you can envision so that you can see why this happens. So, okay, so we actually have a paper about this from 2003. David Corey's, when I was a postdoc with David Corey's group at MIT, we did the first tomographic experiment on a 3-qubit system. Basically, what that means is, you know, we haven't even addressed what tomography is, but basically, you have some box, it spits out a system. You're not entirely sure what happened in the box. I mean, you designed the box, but things go wrong, so you want to know, what did I prepare? State tomography is the problem of using measurements, a set of measurements, a spanning set of measurements to characterize the preparation. Similarly, there's a procedure called process tomography for characterizing the second box, the transformation box. That's premised on the idea that you prepare a spanning set of input states. Spanning what, you might ask? Spanning the space of linear operators. And then you do a set of measurements which span the space of measurement operators, which is basically linear operators on HA. And then from those two sets of experiments, you can remember the box. If we assume the box is linear, I mean, all the engineers know this. I have a linear transformation. How do I characterize a linear transformation? If I know the action on a complete set of input states, I've completely characterized the linear transformation, right? So that's all that's happening in quantum mechanics. It's a set of linear equations on my coefficients. I can characterize that using process tomography. And we did that experiment, and we found that the map we measured was not completely positive. And so we tried to understand what was going on. Was it finite statistics that led to that or not? And it turns out we were confident that it wasn't finite statistics, that it was in fact a nonlinearity in our system. Basically, what happens is, suppose I have a magnetic field which I'm using to generate my transformations. So I have a coupling between my spin and the magnetic field, and my unitary transformation is e to the I b sigma z, or sigma x, right? So where b is the strength of magnetic field, so b includes the strength of magnetic field, the coupling to the, all these parameters, right? So you just put all the parameters in one number b, and that includes the strength of the field. And now what happens is, in general with quantum experiments, you can never do it just once. You have to do it an ensemble of times. And that can be an ensemble in space. I have n copies distributed in space. I do the experiment on each one. Or it can be an ensemble in time. I have one atom trapped in my magneto-optic trap. I do one experiment on it. So what happens is that the control field, the magnetic field you're using to prepare the initial state, might have some error on it. Like maybe the magnetic field is 0.1% stronger than you expected due to the fact that there's some, say, time-varying fluctuation in your electronics. Okay, so then you have a magnetic field that's a little bit stronger at time t1 than it is at time t2. So now, what happens? So I do this experiment. Well, consider the trap, the ion trap example. I have some atom. I want to prepare it in some state. I apply my magnetic field. It turns out at that instant in time, my magnetic field is a little bit stronger than it is on average. So I over-rotate the system. And now I want to apply some transformation to it, right? So my preparation and my transformation are really the same thing. They're both unitaries that correspond to some Hamiltonian. So now I apply the transformation. Suppose that the time scale on which this fluctuating magnetic field fluctuates is longer than the time it takes to do my preparation and my transformation. So it takes me time tau to do the preparation. It takes me time tau prime to do the transformation. Suppose that the time scale on which this magnetic field fluctuates is 10 tau. So then I prepare the state. I've over-rotated it a bit. Now I do the transformation. My transformation will also be over-rotated. Corresponds to an over-rotation. I get my result. I do the experiment again. This time when I do the experiment, my magnetic field is a little bit lower than it was on average. So when I prepare the same initial state, now I prepared a state that's a little bit under-rotated. But now the transformation I apply is also under-rotated, because the correlation scale of the fluctuating field is long compared to the time scale of my preparation and my transformation. So then what happens is now I'm describing a nonlinear situation. The transformation that my system saw depends on the error in the state that I created. So my state is, of course, the state I wanted plus the error. That's the state I got. So the state I got is correlated. The state I put into my transformation is correlated with which transformation occurred. So this is a violation of linearity, which is written here, right? My state rho 1 is now correlated with which lambda I got. I actually have this. I have lambda 1 and lambda 2 here. So when I prepared rho 1, which was an over-rotated state, I had an over-rotated transformation. And, or even a better example is that in case 1, I over-rotated both times. And in case 2, I got it perfect, right? So that you're perfect or under-rotated. It doesn't really matter. The point is it's different. So the point is that the transformation that happened when I had rho 1 is different than the transformation that happened when I had rho 2. That is a fundamental nonlinearity, which is unfortunately physically what happens. But of course, you need very high precision control and to even see this, which is why it's only now that people are realizing, holy cow, this is actually really a problem. And so when you read, like, John Preskill has a great set of notes on quantum mechanics that are online, which you should check out. And his approach to defining completely positive maps is axiomatic. So I derive them by considering, look, I already believe quantum mechanics with unitary transformations in pure states. So let me derive general quantum mechanics from that picture, which is what I'm doing for you. The other approach is to just mathematically axiomatize open system quantum mechanics. Just say, by fiat, I demand that my transformations be completely positive maps. And then show that that's consistent with the unitary description. I don't think that's the right way to do it because you don't see these effects as clearly, that these small nonlinearities that occur aren't apparent when you just axiomatize what you think generalized quantum mechanics should be. But there you assume explicitly the transformation is linear. It takes positive states to positive states, even when you have an ancilla, so it has to be completely positive. And then you get these CP maps out of that picture. But anyways, OK, so I hope that gives you the flavor of why you get these nonlinearities. And then, of course, I mean, that's simple enough. That example is simple enough, and we can kind of understand it. But coming up with a general mathematical framework which accounts for that is very hard. OK, good. All right, now, what are I think I was leading to I wanted to follow up on this comment. So this comment was that there exist better representations of superoperators of completely positive maps than the cross-operator sum decomposition. Historically, this is kind of the first one that was discovered, so people have kind of stuck with it. But when you really think about what's going on, let's forget about this nonlinearity now and just be happy with this kind of provisional description in terms of completely positive maps. Then here's a deep fact that helps a great deal. You're like, cross operators, this is totally new. I have to understand what's going on here in a new way. You don't. This is just linear algebra. So more importantly, the set DH, the set of density operators on H, in fact, more importantly, the set LH, the set of linear operators on the Hilbert space is itself a Hilbert space. OK, so here's a deep fact. When I realized this, everything made so much more sense. The set LH is just a Hilbert space. OK? Now, I told you it's a Hilbert space. It's pretty obvious that it's a vector space, because if I have some operator A, well, let me just, OK, why is it a Hilbert space? If it's a Hilbert space, it's a vector space with an inner product that's complete in the norm. What's the inner product? If I have some linear operator A, and I have another linear operator B, then I can define an inner product AB in Dirac notation as just the trace of A dagger B. OK? So some people, to denote, again, to just as a reminder that we're dealing with a different Hilbert space than the Hilbert space of the quantum state, they put a second bracket here as a reminder. Just like you put a second hat on the superoperator. OK, this is just a mnemonic. We could drop all this and just know what we're doing from context. And so here's our inner product. And then you realize that the map S, I call it lambda, right? The map lambda, which is a map from linear operators to linear operators, is itself a linear operator, which means it has a spectral decomposition and all that wonderful stuff. It has a spectral decomposition if it's self-dual, which is a special case, actually. But what this means is that I can construct a representation. What I can do is I can choose a basis. I can choose a basis of linear operators. let's call that basis B, B sub L. What's going to be the dimension? What's going to be the dimension of this Hilbert space? If H is d-dimensional, what's the dimension of the Hilbert space I construct out of linear operators? D squared, exactly right. So I can have a basis of operators, and then any operator A can be expressed as a linear combination where each AL is equal to the inner product of BL with A, which is going to be a complex number. And so I have this kind of expansion formula. And then in particular, lambda is a linear map, which means I can just construct, if I have a linear map acting on a Hilbert space, even just an inner product space, what can I do? I can construct its standard matrix representation, right? There's a standard matrix representation for any linear map. So I can just do that. And then you have, so lambda has a standard matrix representation. Which is lambda alpha beta. So what I typically do in my course is I use Roman indices for the d-dimensional Hilbert space H, and then I use Greek indices for the d-squared dimensional Hilbert space L of H. So allow me to do that now at the cost of making you change your notes. So let's make this an alpha. Okay, so alpha is an index that goes from 1 to d squared. And then I can construct lambda alpha beta as my standard matrix representation, which is just B alpha lambda B beta, which is equal to the trace of B alpha adjoint lambda B beta. And then this gives me a matrix representation, which is d by d. D squared by d squared. For every CP map. And then I can act on my state. So I have some state rho, which is just some convex combination. Some decomposition in terms of my basis. And then this becomes a column vector. Now my mixed state, am I going too far? Am I going to overwhelm them? My mixed state is now just a column vector. Rho 1, rho 2, all the way down to rho d squared. And my matrix lambda, let me just define this to be my matrix lambda. Then we can just describe CP maps as matrices acting on column vectors because we're doing linear algebra. So then we have, rho prime is equal to lambda rho, where what this means is I have, my matrix lambda acting on my column vector rho. And I get another column vector out, rho prime. And then the way we express this is that rho alpha is equal to a sum over beta, lambda alpha beta, rho beta. Okay, there's open quantum systems. Assuming we don't have correlations between our input state and the environment state that's affecting our evolution. So assuming there's no memory of the preparation in the transformation. Which is obviously it's a useful assumption. We've gotten very far with it, but just be aware that there's a caveat, which is this asterisk, okay? That's very important to remember. Yeah?
You're saying somehow that the purification theorem in the lab doesn't work, right?
Purification theorem in the lab.
Doesn't work.
Purification of what? Of states or of operations?
Of your state.
No, you can purify the state.
Yeah, but in this case, when you're saying that...
Oh, this case.
I mean, the lab.
The nonlinear case. Oh, yeah, the lab with imperfections. And okay, yeah.
Okay.
So it doesn't work. Well,
Then when
I don't know what doesn't work. This purification. I mean, it's this.
If they're correlated, then you cannot write them as a tensor product of two matrices, right? They are correlated. So
If they're correlated, yeah. If they're correlated, you would have a sum in there. Now, of course, if they're correlated, yeah, if they're correlated, you won't get this description.
okay, so if they're correlated, then the purification theorem fails, right? I mean,
Well,
this implies that you can construct a state in a bigger Hilbert space that is uncorrelated.
yeah, you can think about it that way. I wouldn't pick the words exactly like that, but I think what you're saying is basically right. Now notice that we have a purification theorem for states, which we've seen. There's a purification theorem for CP maps, which is called Naimark's dilation theorem. Okay, so I guess I'll cover that next lecture, but let me just foreshadow. Sorry, Naimark is for measurements. It's called Stinespring. It's the Stinespring dilation theorem. I think it's called Stinespring. Which one? I can't remember which name is for which here. Yeah, Stinespring. Good. Stinespring dilation theorem. All right, so let me just tell you Stinespring's dilation theorem, and then we'll wrap up. So let me just recap a bit. We looked at two ways to have generalized transformations. One was mixtures of unitaries. The other was coupling to another quantum degree of freedom and looking at the effective transformation on the system of interest. We're going to work under the assumption that we don't have to worry about the asterisks for the rest of the course. I'm not going to worry about this anymore. Just be aware of it. Stinespring dilation theorem says that basically, so what we came to was that, look, we have this mathematical formalism of completely positive maps. I didn't formally tell you what completely positive maps are, but essentially it's equivalent. Krauss's theorem is that any transformation of this form with this property corresponds to a completely positive map. Any completely positive map, which I have not defined for you, corresponds to a transformation of this form. The relationship is one to many, but the point is this. The set of completely positive maps and the set of Krauss operator representations is equivalent. When I say equivalent, I guess, I'm screwing this up somehow. So how is that equivalent if it's one to many? What I mean is that any transformation of this form corresponds to a completely positive map. Any completely positive map, completely positive means it's linear and positive and completely positive. Any completely positive map admits a decomposition of this form. Just read John Preskill's notes, and he axiomatizes what he means by CP map. It's also in the lecture notes I'm going to give you guys, so you can just look into it. So we have this description, but then the question is, can any map of this form be realized in the lab? Right? That's the question. That was your question earlier, I think. We have a mathematical model which is sufficient to accommodate these two scenarios, but does any mathematical object in this setup correspond to an allowed physical transformation? Stinespring's dilation theorem answers that question and says yes. If you can give me a set of mathematical objects that satisfy this condition, a set of operators AK that do this, or similarly, if I have a linear map, which is also completely positive in that picture, there exists a unitary. There exists some Hilbert space HB, there exists a sigma B, and there exists a UAB that will give rise to that transformation. So if we believe that we can realize any unitary in any state, then we can realize any completely positive map. Any set of Krauss operators. That would imply trace preserving. Right. Right. Thank you. Any set of Krauss operators, by which I mean any CP-TP map, can be realized in basically as a UAB acting on rho A cross sigma B in some extended Hilbert space. Okay, so that's just in words. I'll give you a mathematically precise definition next lecture. And let me just add that this is different from states, right? Remember with quantum states, we said, oh, we can create mixtures of quantum states by just flipping coins and mixing, taking convex combinations of pure state projectors. Or we can construct a mixed state by imagining an entangled state of a composite system and ignoring the second part of the ancilla. And it turns out that set of mathematical objects was equivalent in that any density operator could be realized either way in the lab. I could either just realize it via flipping coins, or I could realize it via entanglement. That's not the case for CP maps. There exist CP maps, which were CP-TP maps even, which cannot be realized via case one. Because as I mentioned, something like spontaneous emission requires that we violate the unitality condition. So that distinction that I made for mixed states, which one of you guys said, well, hey, why are you even bringing this up? Because they're equivalent. Well, it's because when you make the same distinction for transformations, you find that there is a difference. There are some transformations which you can only realize, some completely positive maps, which you can only realize via coupling your system to an ancilla and then tracing out the ancilla. And in particular, the canonical example of that is spontaneous emission, where the ancilla is the electromagnetic field. So if I want to describe spontaneous emission, I need to think about some other Hilbert space, in particular that of the electromagnetic field. Okay, I've gone way over time, so let's just wrap up there, and I'll see you tomorrow.